little bit anxious about the future of refrigerants, maybe you should listen to our next speaker, who's from a company that's way out there in front, manufacturing and selling equipment which uses a refrigerant which has an ozone depletion number of 0 and a global warming potential of 1, only 1. Ann-Sophie Hamel Boisvert is the account manager at Refrigeration Carnot in Boisvert, Quebec. They're already selling to supermarkets. Ann-Sophie is a graduate in engineering, that's building engineering from Concordia University. She's an engineer junior in the L'Ordre des Ingénieurs du Québec. That's the equivalent to the EIT in the Professional Engineers of Ontario. And her title is Refrigeration with Carbon Dioxide. Ann-Sophie?
Thank you. So, our refrigerant name was completely phased out. So if you fast forward to today, or at least the early 1990s, CO2 came back on the table as a viable option because it's non-toxic, non-flammable, has no ozone depleting potential, and it's the baseline for global warming potential. That was after the discovery of the adverse effects of the synthetic refrigerants. And more that we advance in time, more that we see that maybe CO2 is a simpler way to go. CO2 has 3 modes of operation. The only thing that is added to that system would be another valve here that would depressurize the CO2 once the heat rejection is done. The CO2 is depressurized until it's under the curve, so in liquid form. This process will make some flash gas. This flash gas makes the compressor less efficient. When your condenser, you're going to be able to have almost 40 psi of pressure that's going to be able to combat the pressure losses in your system to be able to do your cycle. So this is this is what we use in our computer room air conditioning. So in systems where you need to have some cooling during the cooler months, CO2 would be a great alternative because when it's here is an existing site that we have. We've collected the data. It's in Quebec City, and we have 2 15-ton units, 105 kilowatt refrigeration load. And when it's about -5 outside, you can see here that since only the fans of the evaporator and the condenser are working, you have 105 kilowatts of cooling, and you only have to give your machines about 5 kilowatts. So this is this machine also. It's going to be able to hold its free cooling for as long as the room has its desirable temperature. So if the load fluctuates, then your evaporator temperature is going to be able to go higher. So your outdoor temperature will also be able to go higher, and you're going to be in free cooling longer. We're just going to go back one. So one thing that you should not do when you're comparing CO2 is just looking at the transcritical operation. The colors really don't look good, so I'm pretty sure you can see what's transcritical and what's not. But if you're just going to compare your design temperature of CO2 with your design temperature of another refrigerant when you're doing your design, then you're going to say, oh, CO2 isn't efficient. But if you look more, these are the bin hours of some cities that we took. So if you take the bin hours, then you're going to be able to correctly compare CO2. So you have only a small number of hours that are going to be in transcritical, then a larger number of hours in subcritical, and then a large number of hours in free cooling. The free cooling, of course, depends on your application. If we're talking HVAC, which is pretty much the temperatures here, you would have free cooling for a long time. If you're talking an application where you need really low temperatures, then your free cooling, of course, is not going to be that long because it's not going to be cooler than -20 for a lot of hours during the year. Another place, so first, when you can do some free cooling, you should definitely think about putting some equipment with CO2 so you can utilize the free cooling. Another place where you should think about putting CO2 is when you have some heat recovery at the same time as you're doing your cooling. Because with CO2, since it's higher pressures, you're gonna be able to run some very small lines at a large distance without losing your heat quality. This is an example of a winery where you have to cool your fermentation tanks, and then the building that was beside, it was a bottling plant. So they need to heat their wine a little bit before putting it in the bottles, because if not, then it condenses on the bottle and they can't put the sticker on. So they had a boiler and a chiller that were working independently. But if you use the chiller with the CO2, then you're going to be able to use all that heat, transport it to your other building, and reuse the heat that you were just going to lose from your chiller. This is also used a lot in ice rinks. This here is an example of a project we've made. It's a municipal center. They have 3 ices, 2 pools, a library, and we do the desiccant wheel. So before, they had all these systems in their mechanical room, and when you combine everything to only one system that's going to be working together, you can really see that the room cleaned out a little bit. This is mostly the theory under the heat recovery. Don't know if you can see correctly, but the horizontal line is the pressure, the condensing pressure, and the vertical is the kilowatt heating per kilowatt refrigeration. So depending on when you use your chiller, you're going to have a cooling load and you're going to have a heating load, and you don't want either of them to be working too little or too much. So if you have a smaller heating load at one point, you don't want your compressors from your cooling to work too much. So this is basically what this means, is depending on the pressure of the condenser, your quantity of heat is gonna go down. This here is if you want your medium at about 170 Fahrenheit, you're gonna have only this much heat that you're gonna be able to reuse from your chiller. So all this heat here is gonna be rejected back to the air. But if you can use this heat at 171 and then reuse all this heat here and just preheat some water at 60 degrees F, then you're going to be able to use all the heat that was rejected from your compressor in your system. So this is going to increase greatly the COP of your chiller. Basically here is the pH curve. So depending, pressure enthalpy curve. So depending on the condensing pressure, you can see the quality of, well, the temperature that you're going to be able to get from your heat recovery, and you can see that when you're in subcritical in the subcritical cycle over here, you can have a lot less of the high temperature fluid. So you're going to have to play with your condensing temperatures to see what you really need in your system. So because CO2 is high pressure, you're going to be able to use some really smaller piping. It's going to have to be, well, it used to have to be stainless steel, but now they came up with a type of copper that is also high pressure. So you can use that also, but if you check the copper, the bigger pipe, and then the smaller pipe of stainless steel, you're going to see that since it's so much smaller, the cost is pretty much similar. This map I found quite interesting. I couldn't find a more up-to-date map. This was the supermarkets that were with CO2 in 2015. We started actually the business using CO2 only for the supermarket industry, but we're seeing that slowly other types of market are seeing the benefits of CO2. And you can also see on that graph that we're lagging behind Europe quite a bit when it comes to CO2. They saw the advantages before us, but this is 2015, and in the past 2 years, I'm sure these numbers in North America, they grew quite a bit. So we're getting there. Listen.
Touching on maybe a different subject than what you presented, but can you touch on the safety element that you need to have for putting a CO2 plant?
Yeah, well, one of the things I touched a little bit is the stainless steel that you're piping, because in the standards, you have to have 5 times the bursting pressure for your piping, and since CO2 is, well, we design our systems at 1,720 psi, so the bursting pressure has to be almost 10,000 psi that it has to sustain. We also have some relief valves in our systems that are rated for that pressure. If it comes to safety for, do you mean if there's a leak? So if there's a leak, depending on the volume of your room, you're either going to have only a CO2 detector, or you're going to have a ventilation that's going to get the CO2 out of the room quickly. Because CO2 is heavier, it's heavier than air, so it's going to go down to where the people are working, and they can't smell it, so you have to have your CO2 detector at 5,000 ppm, and then people have to start getting out of the room. But it's all orbital welded because it's stainless steel, so the risks of leaks are fairly low.
Can you locate the mechanical equipment outside the building to avoid these risks?
Sure. Well, you still have to have your evaporator in your room.
Yeah, well.
You can have your compressor and everything on the roof or in another room, but your evaporator, if you have your heat exchanger and then you exchange with like glycol, then you lose the benefits of CO2, which is that it has smaller piping and everything, because you're going to have your bigger piping with glycol.
Well, do you foresee moving equipment out of the room in the future, or moving it out of the building.
That's okay. Here, I'll get it.
Don't worry, she's an engineer. Just as a way of getting around these safety problems.
Is this too much light?
No, that's good.
Okay.
Just with these anxieties about refrigerants, maybe we should move the equipment outside the building, and instead of chilling air, we chill water and pump it into the building.
But what we did with one system, which we did with propane in California, is we did the propane on the roof, and then our other medium was the CO2.
Oh.
So the CO2 was recirculated in the evaporators. And
You can circulate water instead of just, it's not going to...
Yeah, but you're going to need your pump and stuff like that.
Right.
Yeah.
Is this just industrial systems right now, or is there residential systems?
With CO2, we can do some smaller systems because the technology is not there to have like the smaller valves, the smaller compressors. Everything is real, like our compressors, even with our like computer air conditioning, it's industrial type compressors. It has its advantages, but also it's less cost effective to have. And so right now we don't have anything for the more the smaller type systems. Our smallest is about 10 tons.
Thank you.
I got a couple of questions. So you mentioned it's a data room cooling, and then you use it for supermarket cooling. What's your room space set point?
Depends. For
Okay,
the
so
computer room,
right.
room is from 20 C to 30 C.
Right.
Depends
and then
on the room.
supermarket. You're looking at what?
We
Low or
have,
medium?
well, medium temperature is -4, 2 degrees, and then low temperature is -20 to -35.
Okay, and right, and sorry, I lost my train of thought.
No problem.
Okay, thanks.
Did you have a question there?
I did, but you answered it.
Okay.
first time.
Thank you.
Thank you.
Oh, there's another question.
I just had a question about refrigerants generally, and when you look at the risk profile of using refrigerants, there's a lot of comparison made of refrigeration systems in isolation as opposed to in the context and for the operation that they enable, that they support. So, for example, when we look at an ammonia system, it's actually very rare to be able to get third-party liability for an ammonia leak, a catastrophic ammonia leak. Because if you've got a £10,000 plus, you have to evacuate the local town and you don't necessarily get back into your premises. So even though you just get insurance coverage for boilers and precipitors, whereas CO2, you have a sudden release of pressure, a small explosion, but it's contained. And so I'm wondering about the limits of that risk context when planning and sizing refrigeration systems, particularly as we move towards natural refrigerants with hydrocarbons, ammonia, and CO2. Where's the trade-off between these?
Good question.
Well, okay, here's a question.
Well, we're actually supposed to be engineers. We're supposed to help society. We're supposed to do things for a purpose, rather than just fixating on single systems.
Right.
Everything we do has to be for a purpose. Otherwise, it's pointless. So surely we must have some idea of what is the optimum refrigerant to use for a given context.
Well, that's done by regulation by the marketplace.
Well, if you rely on regulation, you're missing the point. We're supposed to harness the forces of nature to the service of mankind.
Well,
come on, there's got to be there's a balance here somewhere.
Yeah. Well, I think regulators try to grasp that, but it's not always possible. Okay, here's maybe a useful question. What sort of insurance do your customers require for these CO2-based refrigeration systems. Is it better than standard refrigeration, or do they have to pay more?
Well, having a leak with CO2 is a lot less damaging than having a leak with another type of refrigerant. It has its security measures because of its high pressure, but I haven't heard of anything that's with CO2 at least. With ammonia it's another story, but with CO2 there's
so just lots of work for engineers in the future. That's all I can say. Okay, well, thanks, Ann-Sophie. It was great. We'll set up the next presentation.